going to start with the purpose of IP addressing. When Bob on network A wants to view a web page hosted on a server on network C, how does Bob's computer know where to send him? Well, somehow Bob has gotten that server's IP address, either in IPv4 format or IPv6. IP addresses are the location of a PC or server or some other network device that identifies it by both its network location and host location within that network. IP addressing provides a logical addressing scheme for our computers so that they can communicate on networks. Being logical means that the IP address can be changed with minimal fuss at any time, unlike the MAC address or the Media Access Control address, which is physically embedded into the device. On the other hand, IP addresses are programmed in and are easily changed. Now that we know the purpose of IP addressing, let's move on to some IPv4 address properties. IPv4 is made up of a 32-bit binary number. That means there are 2 to the 32nd power possible address combinations. That gives us 4,294,967,296 possible address combinations. With all of these possibilities, a process needed to be developed to keep everything neat and tidy, and, most of all, findable. The implementation of a subnet mask was the answer, and I'll get to that subnet mask in just a moment. Something that you will find useful is learning how to convert from binary to decimal. Now, decimal is base 2. That means there are only zeros and ones, as opposed to the base 10 that we're all used to dealing with. If you would like more information on how to convert from decimal to binary or binary to decimal, you can go to that website that's listed under this heading. So now let's talk about the initial properties of IPv4. It is a 32-bit binary number, as I said before. It's divided into 4 sets of 8, called octets. These are separated by periods, or decimals. Each octet is 8 bits, which equals 1 byte. We often represent IPv4 addresses in a human-friendly format that's called dotted decimal. Now, when we look at this address, 192.168.1.9, that is an IP address, but we don't know which portion is the network or which portion is the host. To be able to resolve this, it requires the use of a mask which determines or defines which portion is which. This mask is called the subnet mask, and the subnet mask has the same format as the IP address, as in it's 32 bits and it's represented in dotted decimal format. So let's take a look at how an IP address and subnet mask operate together. So we're going to begin with 192.168.1.9 with a subnet mask at 255.255.255.0. Now the 192.168.1.9 is the IP address, like I said, and the other portion, the 255.255.255.0, is the subnet mask. And it's easiest to show how the subnet masks by converting that dotted decimal back into binary. So we can do that by deconstructing the IP address. So the first octet would be 11 followed by 6 zeros. That equals 192. The second octet is 10101 followed by 3 zeros. That equals 168. That third octet's real easy. It's 7 zeros followed by a 1. And then we have the fourth octet, which is 4 zeros, a 1, 2 zeros, and a 1. That equals 9. Now if we deconstruct the subnet mask, what we have is we have 3 octets that are full of 1s and 1 octet that's full of zeros. That represents that 255.255.255.0. Now if we put the subnet mask under the representation of the IP address, Anything that's not covered by a 1 in the subnet mask is a part of the host address. Everything that is covered by a 1 is the network address. So what we have for that IP address is that 192.168.1 is the network portion of the address, and the node portion of the address is the 9. And that's how the IP address and subnet mask work together to define the network and the node. Let's begin by talking about classes of IPv4 addresses. Internet Protocol version 4, IPv4, is a binary addressing scheme that's used for networking. It was initially finalized as a standard in 1981. IPv4 is a common network addressing scheme that is still being deployed today. There is an issue, though, with IPv4. Because of its structure and the growth and popularity of the internet, most of the world has run out of assignable IPv4 addresses. But thanks to some forethought, it's still a valid scheme today. We need to talk about classes of IPv4 addresses, and we begin with a Class A network address. Class A networks have an address range of 0 to 127 in the first octet. That gives us addresses from 0.0.0.0 up to 127.255.255.255. The first octet on the left has a binary representation that always begins with a 0. This gives us a possible 16,777,214 host addresses, and the subnet mask with a Class A network is always 255.0.0.0. Then there are Class B network addresses. They have an address range of 128 to 191 in the first octet. That means that Class B networks can have a range of 128.0.0.0 up to 191.255.255.255. The first octet on the left always has a binary representation that begins with a 10. Now, Class B network addresses give us a possible 65,534 hosts. And the subnet mask used with a Class B network is always 255.255.0.0. Then there are Class C network addresses, and they have an address range in the first octet of 192 up to 223. That means that we have an address range of 192.0.0.0 up through 223.255.255.255. And that first octet on the left always begins with a 110. Class C network addresses give us a possible 254 host addresses or node addresses. And the subnet mask with a Class C is always 255.255.255.0. The last class of address that you need to concern yourself with is the Class D network address. It has an address range of 224 up through 239 in the first octet, which means that it can range from 224.0.0.0 up through 239.255.255.255, and that first octet on the left has a binary representation of 1110. So the first 4 bits are always taken, and they are always 1110. Now, subnet masks are not defined for Class D networking. Class D network addresses are used for multicast communication. And finally, we have a special class of addresses. Well, kind of a class of addresses. And that involves automatic private IP addressing, APIPA. In some cases, the Dynamic Host Configuration Protocol, DHCP, process may fail. In these cases, a node or host will self-configure an APIPA address. Now, with an APIPA address, the first 2 octets are always 168.254. And if you see that in your IP configuration, you know that you have a DHCP problem. So one of the first methods that they used to conserve the IPv4 address space was they broke them out into public and private IP addresses. Public IP addresses are routable. And being routable means that each public IP address is unique. There can only be one. Now, public IP addresses are not flexible. You are assigned to your network space. You're not really given a choice what your public IP address is going to be. And then there are the private IP addresses. These are non-routable. They do not need to be completely unique throughout the world. They only have to be unique on their network. The first one that we're going to discuss is the Class A license. There is only one Class A license. You have a possible address range of 10.0.0.0 up through 10.255.255.255. Next up is the Class B license. There are 16 possible network addresses, not network and host, but just network addresses available in a Class B license. They have an address range of 172.16.0.0 up through 172.31.255.255. And last but not least is the Class C license. There are 256 Class C licenses, with a possible address range of 192.168.0.0 up through 192.168.255.255. Now, private IP addressing is highly flexible. You get to assign the network space. It's not assigned to you. Now let's move on to classless IPv4 addressing. Now, the classes of addresses actually limited the flexibility of IPv4. Part of the reason for that was that the first routing protocols required the class structure. And you would think that with over 4 billion possible IP addresses that we'd still have flexibility, but we really didn't. Classless addressing, which is called Classless Interdomain Routing, or CIDR, was developed to slow the growth of routing tables. It also slowed the exhaustion of IPv4 addresses. It also created much more flexibility. The subnet mask becomes fluid. It's not rigid with CIDR addressing. It does not affect the private address space ranges, though. Even though the subnet mask is now fluid, you still only have those range of addresses available. And with the introduction of classless addressing, subnetting is now possible and it's highly desirable. So let's take a look at how CIDR notation works. And we'll begin with 192.168.0.9 with a subnet mask of 255.255.0. What that becomes is 192.168.0.9/24. That /24 represents all of the ones in the subnet mask. And that's those first three octets on the left, the 255.255.255. And if you look at that address, it's a Class C address, which always has a 255.255.255.0 subnet mask, but it now becomes fluid with CIDR. We can take it and we can make it a 192.168.128.0/23. And what that really represents, that /23, is a subnet mask of 255.255.128.0. And that gives us a network of 192.168.128.0, which actually gives us a host range of 192.168.128.1 through 192.168.129.254. That gives us 512 host addresses as opposed to the possible 254. Now, the broadcast address for that network would be 192.168.129.255. So now let's move on to subnetting IPv4 addresses. So what is subnetting? Well, subnetting cuts address spaces into smaller pieces. It takes one range of addresses and splits it. This creates flexibility in network design and creates efficiency in address space utilization. So let's take a look at an example of subnetting. And this will involve a small office network. So originally, we have a network address of 223.15.1.0/24. This is a Class C private network, and it gives us a possible 254 hosts available. Why only 254? Well, because a host cannot be assigned the network address, which is 223.15.1.0, and it can't use the broadcast address, which is 223.15.1.255. In this example, with this network address, all the hosts in the network can see all the other nodes. Now let's say that for security considerations, you want to split this into two networks. Well, you can do this using subnetting. So what you do is you take that /24 network and you create two /25 networks. And those would be 223.15.1.0/25 and 223.15.1.128/25. In this situation, the first network's host address range would be 223.15.1.1 up through 223.15.1.126. And why is that? Well, because you can't use the network address, which is 223.15.1.0, and you can't use the broadcast address, which is 223.15.1.127. The second address range that would be created through this subnetting process would give us a host range of 223.15.1.129 up through 223.15.1.254. That's because you can't use the network address, which is 223.15.1.128, and you can't use the broadcast address, which is 223.15.1.255. Each of those subnets would have 126 possible host addresses. So you took your possible 254 hosts available in one network and you broke it down so that you now have two separate networks, each that's capable of having 126 hosts. And that's an example of subnetting an IPv4 address. I'm going to begin by talking about the IPv6 address structure. Now, IPv6 is the answer to the question of what do we do about running out of IPv4 addresses? Unlike IPv4, IPv6 will provide enough Internet Protocol, IP, addresses for the foreseeable future. Now, shortly after the creation of IPv4 and its implementation, the IANA, the organization that's tasked with assigning routable IP addresses, realized the available IPv4 address space would not be enough in very short order if nothing was done. The IANA then set about creating the replacement, and they initially started by working on IPv5. While they were working on IPv5, they found that due to the popularity of the internet, which was increasing at that point in time, that it wasn't going to be enough. So they scrapped IPv5 and began working on IPv6. Now the IANA is confident that IPv6 will function as the replacement for IPv4 for many decades to come. Why are they so confident? Well, we'll get to that here in just a moment. Now, IPv6 works at layer 3 of the OSI model, just like IPv4 does. Layer 3 of the OSI model is also known as the network layer, and its major focus is logical network and host addressing. IPv6's job is to provide logical network and host addressing to devices. IPv6 is a 128-bit binary addressing scheme as opposed to IPv4's 32 bits. The 128 bits are grouped together in sets, with each set being separated by a colon. Now each of these sets is 2 bytes long, and a byte is 8 bits. For human readability, kind of, the binary IPv6 number is converted to hexadecimal, that's base 16, with each hexadecimal number being equal to 4 bits. Now those 4 bits can actually be referred to as a nibble because it's half of a byte. An IPv6 address is 8 sets of 4 hexadecimal numbers, each being separated by a colon. That means that there are over 340 undecacillion addresses available to IPv6. That's 2 to the 128th power, which is roughly equal to 340 times 10 to the 36th power. See that number there? I'm not even going to begin to read that one to you. So now let's talk about IPv6's local address structure. For the local address, the first 64 bits on the left represent the local network, and the last 64 bits on the right always represent the host. The local address structure follows the EUI, or Extended Unique Identifier, format, specifically the EUI 64 format. For those hosts that have a 48-bit MAC address, that 48 bits is actually padded with an extra 16 bits to make it 64 bits in length. You can always tell a local address, which is also called the link local address, as it always begins with an FE80. With IPv6, every device gets both a local address and it gets a global address. Now the global address is unique. There is only one, and every device gets one. The host address is still always the last 64 bits, but every device actually gets assigned to a global network. The network portion is actually composed of a routing prefix and a subnet. This portion of the global address structure follows the classless interdomain routing, or CIDR, convention, with the number that follows the slash denoting the routing prefix. That's the part of the extremely global network that you belong to. The subnet is composed of the bits between the prefix and the EUI 64 host address. Global IPv6 addresses always begin in the range of 2,000 up through 3,999 in that first group of numbers on the left. Now, in most cases, the need for Dynamic Host Configuration Protocol, DHCP, has been eliminated. When implemented, IPv6 will auto-configure both the local and the global addresses that are required for their networks. When a device first comes online, it will use the Neighbor Discovery Protocol, NDP, to discover what the required network addresses are, both the local and global addresses. This allows devices to configure its own IPv6 address without an administrator's intervention. So let's talk about IPv6 notation. The 128-bit nature of IPv6 makes it cumbersome to write out, and it can take up unnecessary space. Because of this, some rules were developed to ease the burden and save space. When you're looking at a group of IPv6 numbers, any leading zeros in a set can be dropped. The thing to really remember about IPv6 is that only a single set of consecutive zeros may be replaced with the double colon. Why is that? Well, because if you could do it more than once, how would routers and other devices know how many zeros to pad in there? Even with this ability to shorten it, it's still difficult for us to remember IPv6 addresses, but it is still easier to write out, and it still conserves space within systems. Now let's move on to types of IPv6 network transmissions. And we begin with the Unicast. Unicast is one-to-one communication. That is where a specific device is sending network traffic to another specific device. Unicast can occur on the local network, which remember always begins with FE80, or it can occur on the global network. Then there's multicast, which is one-to-a-few communication. With multicast, a specific device is sending network traffic to a specific group of devices that have registered to receive that traffic. Routers register to receive multicast transmissions that involve the routing protocols that they are programmed to use. With IPv6, multicast addresses always begin with an FF. Both IPv6 and IPv4 use both unicast and multicast transmissions. A unique type of transmission to IPv6 is anycast. Anycast is one to the closest communication. This is where a specific device is sending network traffic to a specific IPv6 address that has been assigned to multiple devices. The router only sends the communication to the closest one, at least from its perspective. Anycast transmission involves implementing DHCP v6. Earlier I said we really don't need to worry about DHCP anymore, but that's only partially true. While IPv6 is capable of auto-configuring its own local and global addresses, in certain situations that's not always desirable. DHCP v6 version 6 can be configured to hand out specific IPv6 addresses or duplicate IPv6 addresses when necessary. That's useful for when load balancing a network or when network redundancy has been created, or when you have a user that has a tablet, a cell phone, and a laptop, and you want to deliver the transmission to the closest device, the device that he's using at that point in time. That is where DHCP v6 comes in handy. IPv6 and IPv4 are not compatible, but we can do what's called a dual stack configuration. That's where the network and devices on the network receive both an IPv6 configuration and an IPv4 configuration. Or we can use what's called tunneling. There's 6-to-4 tunneling, which is used to encapsulate an IPv6 data packet in an IPv4 datagram, allowing that IPv6 packet to travel across or through an all IPv4 network. 6-to-4 tunneling can also be called Teredo tunneling. Now, let's begin the formal part of this session by discussing the Media Access Control address. All networking interfaces come with their own special address already configured. That would be the Media Access Control address, the MAC address. The MAC address is often referred to as the physical address or the burned-in address of the interface. While MAC addresses may be changed or spoofed, most often it's set by the manufacturer and never actually changes. Now, switches and other OSI Layer 2 devices rely upon that MAC address in order to get network packets to their correct destinations. The MAC address has a specific format. Actually, it has two specific formats. One is 48 bits in length and the other is 64 bits in length, and both of them are represented by hexadecimal numbers. Both formats can be broken down into two parts: the Organizationally Unique Identifier, or OUI, and the Extended Unique Identifier, the EUI. The Institute of Electrical and Electronic Engineers, the IEEE, assigns all electronic manufacturers their own OUI, which always makes up the first portion of the MAC address. Each manufacturer then assigns its own EUI to each device that is produced. Usually it is the serial number of that device. Theoretically, no two interfaces will have the same MAC address. I need to mention the EUI 64 format. IPv6 requires that the node address or the MAC address be in an EUI 64 format, so that MAC address has to be 64 bits in length. If the EUI of the interface is only 24 bits in length, it is actually split into two parts and 16 bits of padding are added to create the EUI 64 format. Now let's discuss the difference between collision domains and broadcast domains. Before I can talk about collision domains and broadcast domains, I need to talk about carrier-sense multiple access with collision detection. All Ethernet networks use this technology, also called CSMA with CD, when transmitting data. In an Ethernet network, all Ethernet devices have equal access to the network media and are capable of transmitting data at any time. This can lead to data collisions. With CSMA CD, a device listens to the carrier signal on the network media. If no other device is transmitting, the device is free to send data. If another device sends data at the same time, a collision is possible, which can corrupt the data. The devices listen for collisions. That's the collision detection part. If a collision occurs, the devices will stop transmitting and wait a random period of time before attempting to transmit again. To do this, they use what is called a back-off algorithm. With that out of the way, now let me explain what collision domains are. Collision domains are an area of the network where packets or network traffic can collide. There are some devices that break up collision domains. They can be broken up by switches, bridges, and routers, but not by hubs. On the other hand, a broadcast domain is defined as all the nodes that can be reached by a broadcast transmission. All the nodes that can be reached reside in the same network. Broadcast traffic cannot pass routers, so the domain is also defined by the subnet mask, and that subnet mask defines the network. Here's a special note. Technically, IPv6 does not use broadcast transmissions. IPv6 replaces broadcast transmissions with multicast transmissions. And what do you know? That's a good segue for us to discuss types of network transmissions. We're going to begin this section by talking about types of IPv4 network transmissions, and first up is Unicast. Unicast is a specific source address transmission going to a specific source destination address. It can be thought of as one-to-one communication. It's only two devices transferring data between each other. Then there's multicast transmission. This is where a specific source address transmission is going to a set of registered destination addresses. This is one-to-a-few communication. Routers often use multicast transmissions to track their routes and to make changes to their routing tables. And finally, there are broadcast transmissions. This is where a specific source address transmission is going to all addresses on the local network. This can be considered as one-to-all communication, because all devices on the local network are going to be able to receive this broadcast transmission. So let's move on to types of IPv6 network transmissions. And IPv6 uses Unicast, just like IPv4 does. IPv6 also uses multicast, just like IPv4. Where IPv6 differs is with anycast transmission. Anycast is where a specific source address transmission is going to a specific IPv6 address that has been assigned to multiple devices. The router uses an algorithm to determine which MAC address that has that specially configured IPv6 address is closest, and only that device receives the anycast transmission.